السلام عليكم ورحمة الله وبركاته. اليوم حتكون محاضرتنا عن Meta Regression in R. هلا أول شيء نحكي عنه إنه what is a Meta Regression. هلا Meta Regression is a type of regression which is an analytical technique to predict an outcome based على predictors اللي هو بنعتبرها ال x axis و y axis. يعني if you guys remember the linear equations from school اللي بتكون إنه slope into the x plus the y-intercept. It's relatively the same idea, and we try to fit our data to allow us to let's say model a line that gives us that slope اللي هو ايش؟ فusually بيكون عندنا ال x-axis اللي هو ال covariate of interest تبعنا، تمام؟ هذا اللي بتغير وبدنا نشوف الافكت تبعه على مين؟ على ال effect size. So ال y variable عندنا بيكون ال effect size. هلا what does the meta-regression actually do? It basically shows us how a change in x correlates to a change in y. Okay? So these are the general formulas for a meta-regression. If you guys remember when we gave you the fixed effects and the random effects model, the fixed effects only contain the sampling error part of the equation. So it had theta plus the sampling error, while the random effects model had that observed theta or observed effect size equal to true effect size plus sampling error plus between study heterogeneity. Okay, so a meta-regression is a mixed effect model. Okay, it has the random effect part and a different let's say modeling equation that I did not really dive into too much. The top one is a univariate multi-regression, while the bottom equation, as you can see, we have two x variables, is a multivariate meta-regression where we use multiple predictors, and as such we need to involve them in our equation. Later on we will also see that we have something called interactions between our variables, and I'll dive into that more when I get there, but we add another variable to the equation. Now, why do we use meta-regressions? Meta-regressions are one of the best ways of measuring heterogeneity for a lot of variables. So if you have, for example, 7, 8, 10 different predictors that you pre-specified when you extracted your data, and you extracted the data for them, and you want to see their final effect on your effect size, you would opt for a meta-regression, as it's an easy and a good way to fix heterogeneity. You can see like it quantifies how much heterogeneity you fixed, as we will see later on. Okay. When do we use meta-regression? Where we use when we need to explain the effect of multiple different variables in our effect size, as I said previously. But something that I did not add, and you guys need to be aware of, that is that usually we would like to use meta-regressions when we have more than 10 studies. So it's very similar to subgrouping, where we have subgrouping is actually a subset of meta-regression. It does relatively the same thing, but and for both of them we need a specific we relatively need a minimum amount of study in order to count the study eligible for meta-regression, and that number is around 10. Now, okay, so we want to use meta-regressions in this analysis. How do we prepare the data that we already have to let's say make it suitable for meta-regression? If you have a continuous variable, you just leave it as it is. That means when we're using the meta-regression, we will be using something called linear regression, where we put or plot two continuous variables against each other, and it will try to find the line of best fit. But what if we have categorical data, for example cancer type, as we will see later on? Then we would need to do something called dummy coding, where we need to code each category and assign it a number. As such, when we plot the graph, it will deal with each category as a number, and R would be able to understand and reflect that in our analysis. Okay. In this slide we will be talking about the random effects model, or like the similarities and differences between the random effects model and the meta-regression. As we said before, the meta-regression uses a mixed effects model, which includes the random effects model. We can notice the main similarity that is present between both plots is that both of them have something called the prediction error. or unexplained heterogeneity variance. If you recollect from our previous lecture, we talked about something called tau squared. Now, tau squared measure, or tau was a measure of variance between, or difference between, the predicted effect, or the predicted effect size, and the true effect size. Okay, so it basically measures the between, the differences in the true effect size between studies, because the predicted size effect is constant. Okay, as we can see, both of them have this prediction error, but you can tell that it kind of, let's say, deals with it differently. In the random effects model, it does not necessarily deal with it, it just quantifies it. As you can see, there is no effort made to, let's say, minimize some of the prediction errors. But if you look over on the meta-regression side, you can tell that the regression tries to find the line of best fit between the prediction errors. It tries to minimize it for each one, accounting for every single study. Okay. Plus, in a meta-regression, it accounts for every single study, and it fixes the errors in the heavier studies. As we remember, in meta-analysis, we give weights to each study, and that weight is based on the sampling error, or the standard error that is present, that is associated with each study, because a lower standard error results in a higher or more precise study. So the meta-regression takes that into account also, and tries to find the line of best fit through the prediction error, while also accounting for the precision of each study. Okay. How do we interpret a meta-regression? When you conduct the meta-regression, as we will see later on in this video, you will have certain results. Now, we will not be necessarily looking or interpreting every single thing that pops up. You need to look at the certain factors that you need. For example, the first factor that you need is the R squared. The R squared tells you how much tau squared your covariate accounted for. Basically, the R squared is a measure of the amount of heterogeneity that you accounted for using your predictor. Unexplained / residual tau. This is the heterogeneity that is left over after we have deducted the heterogeneity that is accounted for by your variable. The intercept is the value of our true effect size when x is equal to 0. This is not that important, but this is just for you to, let's say, have a better understanding of what a regression is. As I explained earlier in this video, a regression is basically trying to find a line, a straight line, through all the points between x and y. And then the p-value. Okay, this p-value basically measures whether or not your predictor has a significant, your co-predictor / covariate has a significant effect on the effect size, or whether it can actually predict your y value or your effect size. We have two types of tests that we usually use for our p-value calculation. It's either the wild type test or the Knapp-Hartung test. Both of these tests follow different distributions, and as we know, most of our meta-analysis is usually not normalized or does not necessarily follow a normal distribution. So using the Knapp-Hartung test, which follows a t-distribution, would be optimal when calculating the p-value. Okay, now the final topic that I will be, let's say, covering in this video is going to be interactions. What are interactions? As I explained earlier, this formula without this variable is the normal multivariate meta-regression formula. But sometimes one of your variables inherently affects another one. For example, as I've written here, location of the tumor can sometimes affect survival outcomes, and for the same cancer. So, for example, assuming we have a brain tumor, a location or a tumor that is located in the brainstem will confer worse survival than a tumor located in the temporal lobe, for example. Now, the patient with the temporal lobe tumor might face other, let's say, impacts that ruin their quality of life. But in terms of survival, which will be the variable or the y-axis that we're measuring, it will not have as significant of an effect as the tumor in the brainstem. So in order to, let's say, quantify this relationship between the two factors, which is the tumor location and the cancer type, we would do something that's called an interaction. Basically, we multiply the two variables, regardless if they're categorical or continuous. We multiply the two variables, cancer type times tumor, because we would be the data would be coded by then, which means we can multiply them. It's numbers in the end. So we just multiply them and then add that new variable that we've created as one of our moderators in R. So that's just, that's how you map interactions, and then you interpret it the same way. Okay. If you guys, or if not if you guys, I think you guys really should read this book that I've attached at the end of the slides, because it's a very important book, and it's going to talk about some common pitfalls that you need to avoid when doing a meta-regression. هلا في some steps that I did not really cover that you should cover when you're conducting your own meta-analysis. For example, mapping out correlations between different predictors in order to assess collinearity. That's one thing, for example, that you guys need to assess and address during your own meta-regression, and you can read it here. You can elaborate on it in this folder. Okay, heck, we're done with our slides. Let us go over to our code. But before we go to our code, I just want you guys to see the data that we have, or the data that is provided for you guys. This data represents gene expression, or the correlation between a gene and its expression with distant metastasis in cancer patients, different cancer patients. And as in the first column, you can see we have author names. In the second column, we have the logarithm of the odds ratio. This is another important point that you guys need to understand, that whenever we're calculating anything for the odds ratio, for risk ratios, we need to use the logarithm of the number. We have the standard error of the OR. We have the country that we got the study from. We have the cancer type that the patients have. We have the specimen source and the detection method. These two are already pre-coded, and these two we will be coding using our code, so you guys can have a general feel on how we can code data and how that translates to our research. Okay, so let's jump into R right now and actually start our analysis. So for today's session, we will be needing 3 packages. We will be needing the Meta-4 package in order to do the regression, as this package is relatively much more well equipped than the Meta package in terms of meta-regression. We will also be using the dplyr package, which is incredible for data wrangling and data handling. So this entire area of code is from the dplyr package, so it's very necessary. And we will also be using the meta package. Actually, no, we will not be using the meta package. Please delete that from your code. Okay, as we all know by now, the first step in our analysis is loading in our data. So we've loaded in our data, and we can check it out and using the variable on the right. So we can tell that this is exactly our data, there's nothing missing, and we want to start by coding the country and the cancer type. How can we do this? We can do this using a function called mutate, and another function that's built into dplyr called case1. Okay, so first thing we do is assign where do we want to save our edits. We want to save it in the same variable called dataframe or df. Then I want to tell it in dataframe. So in dataframe, this piping operator basically says in dataframe, I want you to mutate or change cancer type. When cancer type is equal to breast, change it to 0. When cancer type is equal to GIT, change it to 1. When cancer type is equal to urinary cancer or urinary, change it to 2. When cancer type is equal to oral, change it to 3. And this is a code to handle unexpected cases. For example, if you have NA or not available, then it can handle that and it won't crash the code. For this, we have the same idea. Save it in dataframe. In the variable dataframe, I want you to mutate the column country. When country is equal to China, when country is equal to China, change it to 0. When country is equal to Japan, change it to 1. Okay. Now, if I run, so after we finish dummying our variables, it is time to actually start our analysis. So, as we now all know, the first step in starting our analysis is initiating our variable. Our variable, you can name it m, you can name it mgen, ma, whatever you guys want, you can just name it that. Then we're initializing a new function that you guys probably haven't seen before, the RMA function, which is the random effects meta-analysis function in Meta-4. So instead of assigning random inside of the function, as we did in the meta package, in the Meta-4 package, the function itself is a random effects function. So then we assigned our effect size, yi. It's different syntax, but it's the same. It's the exact same idea, but it's different syntax. So yi is our effect size, SEI is our standard error, that is our dat frame. Our method for calculating the tau squared is ml, because this allows you to compare between different models you build, different meta-regression models, and actually seeing which one is better. If you guys read the source that I added at the end of the slides, you will also be able to elaborate on that idea. That's one of the ideas that I want you guys to read about on your own. And then we have the test, which we already discussed, the Knapp-Hartung test for calculating the p-value between the relevance or significance of our predictor on the outcome. Then this is the new thing that we will be discussing for the first time, the moderators. Okay, these moderators are the variables that we will be testing in our meta-regression. Okay, so after we've written our code, we can just run the code, and we can inspect the variable or the code itself by just writing the name of the variable and then clicking Control Enter. Okay, so after you do that, you will get a screen, or you will get these results in your console. First thing that we can look at, or that I like to look at, is the R squared, which we have already discussed and said that it is the R squared represents the amount of heterogeneity that you accounted for, like how much of the heterogeneity that was originally present was because of your predictor. So in our case, when we used cancer type and country, we accounted for 22.64% of the heterogeneity, which is not bad. It's actually relatively pretty good. But given the very high, residual heterogeneity, as you guys can see, the I squared, the residual heterogeneity is 70.37%, and the estimated amount of residual heterogeneity in terms of tau squared is still more than 0, so it's still relatively high. Okay? Now, the model results, which will tell us how our predictors individually affected the outcome, you can tell that in terms of cancer type and country, neither cancer type or country p-values were significant. Okay, that means we did account for some heterogeneity, but in like their actual effect, or the effect of cancer type on the predictor itself, is not significant. So cancer type does not necessarily affect the OR, or the odds ratio of developing metastasis, but it did account for some of the heterogeneity that was present in our study. So that is how we interpret meta-regression. Of course, you can do a lot more with this, but you guys can read the book that I attached. At the end, it will allow you to explore different avenues. There's still comparing different models and seeing which one is the best predictor. You can still plot different models, etc. But in terms of writing a paper, all you need to do is mention that you guys conducted a meta-regression, list the main results that you guys got. You know, it's not significant in terms of effect size, but it did account for some of the heterogeneity. And that is it. And with that, we have conducted and ended our session. Please head over to Jehad's YouTube video to watch how to conduct a network meta-analysis. Thank you very much.